is that, okay, the basic principles that are using seismometers, traditional seismometers, are inertial instruments. So they are based on the harmonic oscillator and damped and forced that you should have discussed during the wave physics course or in other similar courses. So we will start discussing briefly and quickly the idea of an inertial instrument to understand that every inertial instrument owns a specific response as any other linear filter. So we will see some classical instruments just by, okay, how to say, sort of a historical background, but also to understand that traditional original magnitude had been defined using one of these. The last definition of magnitude actually will use, in principle, just theory and the theory that we have been discussing. And then we will try to conclude this quick part, this quick view, with the idea of modern instruments that are called broadband. Maybe in Stefano Parolai's course, you're going to discuss modern instruments from a different point of view, maybe something about accelerometers and or Borel instruments. So this lecture today does not represent a course on seismometry. No, this is theoretical seismology course, but it's just a bridge that is going to move us from the clean but complex world of theory of the kinematics of a source, and will move us to the last part that is about application of this theory. One of the applications will be the measurement, the modern measurement, or the idea to measure the size of an earthquake. And then during the next week, we will discuss some other application that is about seismic and tsunami hazard, and some, again, maybe a too quick lecture or idea about inelasticity. So this is what we're going to discuss today, on Friday, about earthquake size, and for the next week. Sorry if I will be quick through these 40 slides here, but it's just to have an idea. So no, how to say, desire of completeness here, just a quick view. So let's start. For this maybe a relaxing lecture, a little bit more relaxing than the previous ones. Okay, every lecture or discussion about the instrument should start from this, that is supposed to be one of the first, and maybe it is one of the first instruments to measure something from an earthquake. But we cannot call it a seismometer. We can call it as something that is revealing the effect of an earthquake. That's why it's called Seismoscope. Its Chinese origins make it very fascinating. Actually, we don't have a clear understanding of what was inside that pot with dragons, frogs, and bulls. Maybe there was a system of pendula, but in any case, the idea is that if there is a shaking, it's going to reveal it and maybe giving an idea of direction from the, of course, from which the wave field was coming. So this is a seismoscope, but actually the classical instruments that can be called seismometers or seismographs, they have a sensor, could be a pendulum, that's fine, could be a mass and a spring, could be a combination of them. And then there is a recording system. And traditionally, the idea was that, okay, the main difficulty was to join the sensor and the recording. Because, for example, you need to have a pen that is writing on a drum of paper. But for example, the Wood-Anderson, that we will discuss in one slide, actually was based on the idea of a ray of light that was going to leave a message, a sort of a written message on photographic paper. But one of the difficulties was to connect the mechanical sensor that is based on an inertia principle to the recording system. Nowadays, this is overcome by modern sensors that are tiny. We have some sensors also inside the smartphones because they have accelerometers inside based on what we can call MEMS technology. So they are very tiny. And the recording is now digital. You can use Wi-Fi, you can use satellites, but at that time, the idea was to have a sensor and a recording system. And one of the very simple ideas is that what we have to record is the ground motion. It could be recorded as a displacement, as a velocity, or as an acceleration, especially for high frequencies. Please do remember that okay, here I'm going to say something very basic, very trivial. If we take a nice and plain wave, okay, we have to add spreading, we have to add an elasticity, let's wait for the next week, whatever. But every time, if this is x of t, velocity will go as omega, because we have a time derivative here, and acceleration will go as omega squared. What does that mean? That if we move from a displacement to velocity domain, the signal is getting richer in high frequencies. And we will see during the next week that high frequencies are more damped than the low ones. So usually acceleration is the domain of the near the source domain. That's why accelerometers are usually used for strong motion, whatever it means. It had a classical definition, but if you're going to listen to strong motion seismology, usually they are connected to accelerometers and accelerometers. By the way, here we just need to understand we need to record the ground motion, but it's a vector. And since it is a vector, the most natural choice is to use a sort of a geographical system, because we cannot rotate the sensors whatever the source is moving. No, that's crazy. We cannot do that also because we have uncertainties. So usually we have two components, north, south, east, west, and the vertical one. Now, just recalling in 1 minute some theory about waves, we know that, okay, P waves are longitudinal, so they can have a component in all the directions. S waves are transverse, so according to your orientation, the wave field will be done in a different way. But surface waves, like Rayleigh waves, like Love waves, they are P and SB, radial and vertical, and Love is just transverse. So the idea, and this is one of the very simple idea that is at the base of many applications, is that in the vertical component of a motion, there should be Rayleigh waves. And we will see how they have been used, and they are used in the definition of magnitude on Friday. Okay, by the way, that's the idea. A pendulum, mass and spring, and so we know the theory, and we are going to see now the equation in some idea in its classical shape, that is the forced, damped harmonic oscillator. Okay, the word these slides, I leave them for your reading. Let's call it homework. But the key word for the classical instruments is inertia. And whatever you use, if it is a pendulum, or if it is a mass and a spring system, or a combination of this, we have to remember that every oscillator has a sort of natural frequency. It could be due to the length of the pendulum and gravity. It could be due to the spring constant and the mass, but whatever, we have a natural frequency. And if you remember during the last lecture, I was shaking my power plug here, and I had been forcing it at different frequencies, getting different amplitudes with the same forcing. With the same amplitude, I can get different answers because it depends if I'm near to the natural frequency or longer or shorter. So the idea here, inertial instruments have a specific transfer function. Or if you want, a different Green's function. Remember, the Green's function is the delta excitation of the inhomogeneous problem. And for example, if we write the equation of a damped, forced oscillator, actually we get the equation of a seismometer. What is the difference here? And usually it's called indicator equation. But it's nothing else than a rewriting of the harmonic oscillator equation that you should have discussed during the wave physics. When I was doing wave physics, the first lecture was about harmonic oscillators. And, pardon?
We didn't.
No, I can't believe you.
So my friends can
okay.
Join me.
Okay, let's make it in 30 seconds.
Yeah.
That's Newton, right? That's a mass in the spring. Let's couple Sir Isaac Newton with Sir Robert Hooke, right? Okay, that's Hooke's law. You did it. Am I right?
Yes.
Yes.
Thank you.
Yes, you're right.
Okay. Okay, if you couple them, you get this. Now you did it. Okay, that's the harmonic oscillator. And you can write its solution. Is it okay?
Yeah, it's okay. I just wanted to tell you that we
okay,
didn't.
Wait, one part is missing here. Damping. Let's imagine we have friction there. So now we have to enrich it. And now we have a damped oscillator. And here the amplitudes are decaying in time with a rate that depends on damping. You did it. We have been doing it, right?
Yeah.
Okay, now we have a problem. This is the homogeneous equation. And I can play with it, okay? With initial conditions. Initial conditions will decide the amplitude and the phase, okay?
Yes.
Okay. Now the problem is that we are forcing it. Do you want to take the Green's function problem? Okay, you can put a delta t. And you can solve it. And if you know the Green's function, you can call it the impulse response of the system. You can take its Fourier transform, and you can call it transfer function. Okay?
Okay.
Good. Now, the forcing of this system here is the acceleration of the ground motion. That's it. So here, that's the acceleration of the ground. Okay? Or me shaking the pendulum. We can rewrite that equation in a canonical form And we have where G usually stands for amplification of a system. And this is just a rewriting of this equation for a forced damped harmonic oscillator. Now, where are the parameters, the key parameters here, here, and here? Damping, but you can, usually it's assumed to be a sort of a viscous Newtonian fluid. That's why usually we put a damping term that is related to friction, or when you have to charge the pendulum that is measuring time, because in the classical clocks, you have to charge it. You have to charge also the digital ones, okay? Because we have friction in some way. And whenever we consider classical friction, we put a term that depends upon velocity. That's Newton, but not Newton as a force, it's Newton as a Newtonian fluid. Viscosity, next week. Okay, what is the solution here? We should know it. It's a problem that can be easily solved using the Green's function, using Fourier theory, whatever, we know it. But now, what we want to measure is U given X, because that is what we want to measure. Okay, and if you develop the theory, what you get is that the amplitude of a response in the Fourier domain, in its general term, is this. And the phase is that one. Now, actually, I'm sorry, I will appear very ridiculous here, but let's try to do it again as an experiment. Okay? Now, that's it. In this case, we don't have a spring and a mass, but we have gravity force and the length. I can start with the initial condition, and the period is given by its length and the gravity acceleration in this place here. It's one of the ways, if you're using pendula, you can measure gravity knowing the time and the amplitude. But today's is a different view. Now, what if I force it? Okay, I can force it at very high frequencies compared to its natural one. You see that the amplitude is not that much, because actually the frequency of a forcing is much larger than omega 0. What does it mean is that the time derivatives will prevail here, and so what we are getting here is that these two terms are prevailing. It's like if omega of a forcing is getting much larger. You can take the limit here. Omega 0 is too low, and it cannot follow. So the inertia is making it almost stable there. But its tiny response is proportional to the displacement, because you have a second derivative. What you're recording is the displacement of my hand, of course, at very tiny amplitude. Now, what about the phase? Actually, it's not able to follow. It's always out of phase. And actually, if you take this term here, you will get a phase of pi. Now, what if I force it at very low frequencies compared to its natural period? Oh, it's following. No phase, almost no differential motion because it's able to follow. Now the displacement is take the role here, and what we're measuring is the acceleration of the motion with, of course, a scaling factor. Usually the transfer function of the harmonic damped forced oscillator is mapped through two plots of these two functions here. And this is what I was putting here. And the picture on the top that is showing amplitude is in many cases called resonance curve. And what it's saying us, okay, usually the larger amplitude is when we force the system near its natural frequency. So very long period, very high frequency, but if I force it at its natural one, oh, I'm getting large amplitudes here with a tiny motion of the hand. That's a resonance. The amount of amplitude that we can measure depends on the damping. In principle, in this expression here, if we put zero damping, but that's not nature, that's an idea, we get an infinite response when we go at omega 0. You can imagine to make the experiment with a friend on a swing. You can push him or her very rapidly, and the swing will not move. You can swing it very slowly, but no fun there. But if you put a forcing very near to the period of a swing that depends on the length, you can kick your friend to the moon, in principle, if no damping. You would get infinite amplitude. That's an ideal, not a realistic case, because we have always damping. So, and we want it. Otherwise, any oscillator would move for the first pushing, and we don't want that. So damping is there. Damping is causing the width, is deciding the width of the resonance curve, and of course, the out of phase depends. If the forcing frequency is very high, it's going to pi, or very low, it's going to 0. At resonance, it's pi over 2. So that's the idea. And that's it. Here I put some words to explain what I was showing to you with my ridiculous experiment here, but I hope that you get the message. Now, we can do this with many systems, but what we want to do is try to record seismological frequencies. And here we get a problem. And the problem is that we would like to measure relatively long periods. How much? Well, let's say 10, 20, 30, 100 seconds. Those are the periods for, let's say, global seismology. Now, 20 seconds. Oh, if you use a mass in the spring or a pendulum to get tenths of a second, you would need 100 meters. Okay, you can go to the giant cave here. Maybe you will go, that depends on the emergency situation around here, but we can go. Every year, usually there is a trip to the giant cave. I don't know if this year, I hope it's going to happen, maybe later, between spring and summer. But you can see a beautiful pendulum of 100 meters. But we cannot build everywhere a 100 meters pendulum, and we cannot go on the field with 100 meters. What was the idea? It can be summarized with the word aesthetic, also if that's much deeper. But for us, the idea is, okay, let's find a trick that we can get long periods with normal lengths. Now, that's the period of a pendulum, an ideal one. With damping, it's a little bit lower, but let's say that's it. Now, to go long periods, we need a long L, or we can diminish G. Well, we cannot diminish G, that's nature, that's the Earth. But maybe we can play with that, with some frames that are tilting the pendulum, and the idea is this one, so that the effective force on the pendulum is smaller. And that was the idea. Because if you use a frame like that, and that's called garden gate, because it's like a garden gate, okay, you can play with angles, with tilt angles, diminish G. And so instead of using 100 meters, you can use 20 centimeters. That was the idea of building instruments, let's say at the beginning, at the end of the 19th century, beginning of the 20th century. And we will see now, I'm not an expert, so please don't ask me how actually the design, the mechanical design was so nice, but don't ask me more than I was putting on these slides here. Based on this idea, the classical instruments have been developed to measure the long periods of seismic waves. Okay, this is another sketch coming from the Villen textbook. It is a sort of a holy book about instruments here. And on this idea, also other instruments have been used and developed also to measure strains, for example, the formation of the Earth. Okay, nowadays we can use GPS. Good. At that time, these were the best. And on this idea, one of the first instruments had been built, and you see here, this one in Germany. There were many also in Italy. I'm not going to say that there was a competition, but actually Italy and Germany at the time were very good at building. Why Italy? Well, because there were many earthquakes here. By the way, officially, this is the first recording of seismic waves. We're in Potsdam. It's also the place of the GFZ. Nowadays, you can ask Stefano Parolai news about GFZ because he had been working, he's cooperating with GFZ there. By the way, on this beautiful frame with a mass, with a beautiful mechanical system, this was the first record. And it's nice, isn't it? Okay, nowadays, we can't work with this. We don't know how to do it. Also to take maybe a Fourier transform of this, because we should need pencil and paper here. Of course, we can digitalize it, but you see that it was there was the drift of the very probably of the earth tides, the solid earth tides here, but it's really a romantic signal here because it was coming from Japan. Okay, so you see that's the idea, and on this idea, the next step, why it's not working here, was now going on the other side of the world, and some German researchers had been cooperating with the Japanese ones, and they built this other beautiful piece of machinery here that is called the Bosho Mori. I found these old pictures here. I hope you like that. You see that there is a pen here writing on a drum. Maybe some of them, they were also using beginning to use some rays of light and to use mirrors to get a signal far from the instrument, but they're really nice. And what you see here is the recording of a San Francisco earthquake. That is a famous earthquake also because Wright, looking at the observations, analyzing the observations collected on the field, he had been formulating the idea of elastic rebound. By the way, going on the other side of the Pacific, okay, this was the recording of a San Francisco earthquake, but in Tokyo. So that's the idea of mechanical inertial instruments. Another German, if you go to OGS, there is also, it's at the entrance of one of the buildings there, but this is a huge mass to go to long periods, and it's rotating on this very big lever, whatever. Don't ask me more than this. I don't know. I'm working with equations, so I don't know. But it's beautiful. And in US, Mr. Wood and Mr. Anderson developed this one. It was based on a different principle because it was a torsion seismometer. It was using a ray of light. It was writing on a photographic paper. But why I'm showing this to you, and that's why we're here today, because this was one of the instruments that had been building the seismic network in California when Charles Richter and Benno Gutenberg had been working. They were probably the most famous seismologists at the time. They had been analyzing a huge set, well, a relatively huge set of data. And using the recordings from this event, from this instrument here, they developed the idea of magnitude. That's why I'm showing to you these slides here. So message to take home, and we will develop it a little bit, is, okay, the first instruments were based on the inertia principle. Let's remember Hooke's and Newton and the forcing. And the first recordings appeared because before it was the realm of theoretical seismology. Laplace, Cauchy, Green's, whatever. Okay, first message to take home. Using the recordings from a network in California, relatively high seismic, well, high seismic activity there, trying to classify earthquakes. That was the basic idea. Is it okay up to now?
It is okay.
I have just a little question.
Yes.
Before, what magnitude they were using before the?
No magnitude here.
No magnitude yet.
Still to be defined.
Okay.
We don't have it. You have to wait for Friday.
Okay.
This is a bridge to Friday's lecture about earthquake size, as I told you. So here we're going, okay, we have to walk up another hill on Friday. It's a nice one. It's not that bad. Not bad. All of them are beautiful. The Friday's one, okay, it's not that difficult. Today we are taking a tour, okay? A sort of a nice trip to see around. We are going to relax today. But what we have to take home is this postcard, because we are going to use it in one slide on Friday. But no magnitude now. Still to be invented. Still to be defined. We're in the 20s here, and magnitudes had been defined after the 30s. Okay?
Okay, thank you.
Okay. Let's go on and let's try to make another visit to this museum, if you want, of ideas of instruments. And why I'm showing this to you? Well, because you see, it's beautiful. Actually, some of them are still in use today, vertical and horizontal ones. I remember that I was visiting, I put a slide later. One, I took a picture in Moldavia a few years ago. And when I visited Cuba to meet my seismological, the friends working there, they were using the Soviet instruments, and still they're using instruments similar to this, plus modern ones. But the idea is still there. You see a beautiful spring, everything is nice here. What is just the tiny difference here is that they were using a ferromagnetic material as an inertial mass inside a magnetic field. So you're much younger than me, so you can remember better one of the bricks of the Maxwell equations, and you can remember that there is a motion inside a magnetic field. Okay, you're going to generate a current, and the current will be proportional to velocity. And that was the idea for Sir or Boris Galitzin. Well, not Tavarish, because still the revolution had to happen. But now, if you have a piece of wire, you can take that signal far from the instrument. And that was the idea. And this idea is still active today. So we can use an electric signal as a proxy to the motion. So we don't need to follow a pen on the drum or a ray of light with deflections and mirrors, but you can take a current. And of course, after the 60s, you can use all your beautiful theory and practice of electronic circuits to manipulate it. And that was another revolution. So that's why I'm putting here this picture. And that's the summary up to now. Because then, at that time, let's say that we're now in the 40s, after the Galitzin mechanics, that's the summary of an instrument. Inertial mass, maybe inside the magnet, a magnetic field. So we have a wire here, and we can move a signal out from the instrument. Ground motion, so we know everything. What we have to remember is that all these inertial instruments have a transfer function. So if we take the Green's function, or if we take the function as before, it has a peak around its natural frequency, of course. But what that means is that to measure different frequencies, we need different instruments. And that's why this is a sort of a collection of the classical instruments and response curves. We know that if we want to measure long period ones, we need LP instruments. If you want to use short period, let's say 1 second, we need short periods instruments. And that's why what was called, and we're going to discover now very quickly, one of the first seismic networks was based on a set of 2 triplets, three components of long period and short period instruments. And this is what we're going to develop now. Because we have to remember this acronym here, we can call it WWSSN. Now we're in the 60s. And 2 things, let's say 3 things were happening there. Well, after the Second World War, maybe you're young, but you should know part of the history, there was the Cold War. And the Cold War was meaning also a huge deployment of seismic instruments. Well, yes, for science, but especially to measure the power of the nuclear explosions on the 2 sides. I'm not an expert of that. There is a branch of seismology that still is studying nuclear explosions for Pacific, with a peaceful idea, and it's located in Vienna, it belongs to the UNESCO. It's called CTBTO, if I remember, I'm not part of that. But by the way, what does that mean is that we have a worldwide seismic network, and this is one of the pictures. Well, you should say, wait a second, that's not the whole world, it's half. Oh, yes. But actually, there was also another network on the other side, but the acronym is referring to this one. But of course, in the 60s, many seismic instruments were around the world. There was also one in Trieste because the border was passing here. So, number of instruments. Second, computers. Well, maybe they were giant ones in the sense of that they were filling a whole room, but the idea of processing data and to compute Fourier transforms. So that was the second revolution. And the third one, if you want, is connected to that, is that digital information was starting to be created, so with bits. So that's why instrumental seismology, compared to historical or theoretical seismology, had a boom in the 50s, in the 60s. And that's why one of the papers that I left you about new, modern, new global seismology, seismology and plate tectonics, okay, it was based on the recordings of earthquakes in the 60s. Okay, what was a standard? So worldwide, seismic standardized. What does that mean? Okay, but now we can share data coming from similar instruments. And how it was done, okay, this was, oh, sorry, it's a little bit slow. I've been able to find these pictures of the classical instruments that were deployed in a typical station of the WWSSN. And you see, there are the long periods one, WWSSN, the short periods one, you see, that's the second, so 0.1, 100, the two extremes. In one of the last slides, I will show to you now the modern range of seismology, but this was the situation, and this means, okay, instrumental seismology, in the sense of seismic recording, starting to be accumulated and shared. Shared, well, yes, worldwide, but there was the curtain that was separating Eurasia. But on the other side, there was another network. These are the pictures that I was collecting Kishinev, or Chisinau. Nowadays it's in Moldavia. At the time it was part of the Soviet Union. And these are the pictures that I was taking in one of the, let's say that they are part of a worldwide standard network, speaking a different language with different response curves, but the idea was the same. And you see two triplets, two horizontal, a vertical, two horizontal, a vertical, short period, long period. That's the idea. The basic development of classical networks that were very modern, because now we are reaching the 70s. And the 70s, the late 70s, let's say 60s and 70s, are the periods in which the definition of magnitude changed. And we will see that on Friday. So just to answer again to your question, from the Richter one to the 60s, 70s definition of other magnitudes, and they are called body wave magnitude and surface wave magnitude, and you should imagine why. So let's say long period, short period, accumulation of data. And then we will see on Friday what's going to be, not the end, but sort of the Hollywood's end of this story with moment magnitude, because new data arrived, a lot of data. Okay, what's the next step? Well, some other transitions now going that are allowing us to move towards modern seismology, let's call it modern instrumental seismology. The first one is so trivial for your generations, but it was not in the 70s. Computers processing data, network, internet, okay, the early days, late 60s, between UCLA and, I don't remember, it was Virginia University. So first messages by network. If you want to see a beautiful story, you can look at the docu-movie by Werner Herzog that is called Lo and Behold. You can see the first, I don't remember if it was a VAX system, but it was a box, a huge box, that was able to transmit at thousands of kilometers the first messages between computers. So if you want the start, not of the web, but of the internet. So that was the revolution, that was the time of a digital revolution. And what does that mean? Okay, the idea is here, because you can move from analogic signals, pens on drums, pictures with rays of light, to bits. And so digital seismology is based on data that is based on sampling and number of bits in amplitude. I will be very quick now to develop this idea with some, how to say, application that was crucial at the beginning of the digital era. But nowadays it's so relaxed that no one maybe is taking care about that. But since here we are at a sort of a theoretical seismology course, let's think about the concepts that are behind a digital signal. I'm sure that you have been taking courses here about, I don't know, signals theory or calculus, whatever, computer exercises. So the digital idea should be with you, but we have two consequences here. The first is that now we are sampling a signal. Oh, so you could say good news. So now we have digital signals. We can process them. We can use FFT. We can do whatever in one snap. Now, maybe with Python, you can do whatever. In no time, you can accumulate, read, manipulate, amplify, deconvolve, whatever in one snap. You have everything. But in the early times, the digital signals, good news because we can store signals, maybe on tapes, and still we have at my institute, we have boxes of tapes, floppy disks. They are so nice now. But wait a second, because at the time, memory was not, so common. So gigabytes were far to be seen on the horizon. So there was an idea here that is about sampling. That's why I want to spend a couple of minutes. I'm sure that it's a sort of something that you have already been studying here, but just to be clear, I want to discuss just a little bit with you about Nyquist frequency. Because now let's imagine that we have a signal. Let's imagine this is an amplitude. Maybe it's the ground motion, maybe it's displacement. Okay, we have something like that. And in nature, this x of t has infinite values. It's a continuous function of time, of course. Now we have to store data, so we have to sample it. Now, how many samples a second? Well, you could say, well, let's take as dense as possible. Wait a second. As dense as possible means a huge amount of data. No. Wait a second. Well, you can say, okay, let's take 1 per second. Everything depends on the frequency that you want to record. Because every time that you take a signal, a continuous signal, and you sample it, actually, you're multiplying it by a set of deltas. Because this function here, let me collect a new piece of chalk. Because actually, we are multiplying the initial signal by what is called a comb function. What is a comb function? Well, I don't use combs, as you can imagine, but a comb function is a set of deltas spaced by delta t. Okay. Okay, this is what we want. But wait a second. If delta t is too small, we have a huge amount of data, and maybe we can reach that delta t. On the other side, if delta t is too large, we are missing part of the data. How to manage that? Okay, now we use the convolution theorem, and what we get here is that in the Fourier transform domain, this is, okay, let me be creative here. This is what we want. And the Fourier transform, what we get here is the spectrum that we want, but convolved by the Fourier transform of a common function. Now, what is the Fourier transform of a common function? Am I alone here? Yes. Is anyone out there in the space?
Yes, it's a flat spectrum.
No, sorry, my question is, what is the Fourier transform of a common function?
I am trying.
Well, my friends, you know I don't use comps. You should know. Okay, it's a comb function.
Yes.
But with spacing 1 over delta t. Now, this is the sampling step. This is the sampling frequency. And maybe if you go to disco and if you listen to techno, maybe you are used to know some bytes per second, BPS. If you're producing music, you should know what is a BPS. Okay, that's it. The number of samples per second. Now, we are not listening to music here, but there is one consequence here. That convolution means that the spectrum that we get, I will go on that part of the blackboard, will be the real, what we want spectrum, because we want the spectrum of X. It may be, I don't know, it's something like that. But it's convolved by a common function with a spacing of 1 over delta t. And this spacing here is 1 over delta t. So we have duplicates, we have phantoms, we have aliases. And what does that mean? That you can say, okay, we don't care. We make a filtering and we can use this one. Good. But if delta t is too large, 1 over delta t is becoming too small. And maybe they overlap. And we have the aliasing problem. That's why when you listen to anti-alias filter, it's trying to avoid that. Now some everyday's, or almost everyday's effects of this is, if you look at a movie, a Western movie, with the old video cameras moving it, the wheels of the chariots appear to go back. Or if you look at a movie where there is not a modern LCD monitor, but with a cathodic tube monitor, in the movie, it's flashing. Or, well, there are many alias effects. So the only way to avoid aliasing and to see frequencies that are not real, because they are fakes, is to have a delta t sufficiently short that the aliases are not overlapping with the original spectrum. That's why the sampling step should be small enough. How much small? Well, to avoid overlap, the alias and the original spectrum to be out of them, it means that the F max that you can reproduce efficiently has to be less than 1 over 2 delta t, because we have to be separated. It's called Nyquist frequency. So if you want to record a seismic signal up to 10 hertz, your sampling should be at least 20 times a second, at least. If you want to listen to music on a CD, digital music, nowadays you're using MP3, I know, but if you want to buy a CD, you have to take care that we are able to listen until 20 kilohertz. And then the sampling of digital music, well, actually, common ears are not able to solve very nice, very high frequencies, but let's say 20. That means that your sampling for digital music should take care about that, and the number of samples should be at least twice. Then there is a factor of 2 just to be safe, and that's why a traditional audio CD is containing about 700 megabytes of data with that sampling. If you ask why 700, because legend says that the CEO of Sony at the time was so in love with one of the symphonies of Beethoven that he wanted that the duration, I think the 5th symphony of Beethoven, should stand on a CD. That's why 700 megabytes around. But it's another effect of sampling time, but that's for acoustic signals. For seismic signals, if you want to go to 10 hertz, you have to sample at least 20. Nowadays, no one cares about that because we have so tiny sampling times that we have to desample data. But originally, that was not the case. And the second effect is that the early days of GPS, let's say the 80s, the sampling rate was 1 sample per second. And that was, wow, it was to measure fixed positions. So 1 was okay. But that was not the domain of seismology. But nowadays, GPS can have very large sample times, very small ones. So you can easily go to 10 hertz. So this is one of the effects of sampling here. I know that you don't think about it, but it's there. So when you listen to the Nyquist frequency or aliasing, alias effect, anti-aliasing filter, that's why. So digital one. Second consequence is the number of bits that you are devoting to record amplitudes. Oh, that's another effect. And you can say, come on, we have so plenty of bits that we don't care. Yes, but at the beginning of a story, that was not the case. Because to devote bits or bytes to amplitudes was expensive. And so, for example, if you're using 2 bits, you can record, it's a matter of sampling the amplitude. So now it's a matter of, if you have 2 bits, you have 4 digits, so you have 4 levels. If you have one bit, you have 2 states, 1, 0, 1, 0. So it's overcoming, this signal would be like that, 0, 0, 0, maybe 1, 0, 0. So you're losing details there. So the number of bits for an instrument is important, devoted to amplitude, for sampling there, was deciding what is called dynamic range. And the dynamic range is measured as the ratio between the largest amplitude that you can record and the smallest one. That's why if you are going to work with instruments, you have to remember that there is a formula that is connecting the number of bits and its dynamic range. So for example, 2 bits, 4 bits to do a fourth. So you're increasing the sensitivity of your amplitudes. And if you want to measure the dynamic range, okay, it's a formula very similar to what we use in acoustics, for example, to measure sound intensity level. the idea is always the same when you use logarithms every time that you want to squeeze large numbers, powers. The same idea applies to acoustics. Have you discussed it in wave physics? Make me happy. Yes. Okay, so you know the definition of a decibel for acoustics is 10 times logarithm of I over I0, or 20 logarithm of amplitude, sound pressure level, respect to the lowest value. Let me write it, because actually Richter has been developing just that. Now this is called sound intensity level. And the idea here is to define a threshold it's an intensity, so it's the energy over time over a surface, over a unitary area. So it's measured in watts over square meters, and it's used also for our eardrum. Okay, this on average is the threshold level. If a sound exists, but its intensity is lower than this, we cannot hear it. Maybe a bat, dolphin, they can, but we can't. So you take every intensity, you compute the ratio respect to this one, you take the logarithm, and you multiply by 10, decibel. So for example, the acoustic range is between 120 and 0 decibel. Why 0? Because that's I equal to I0. Why 120? Because at 1 watt per square meter, we are beginning to feel pain, mechanical pain. And 1 watt over square meters means here at 12, 12 is going here, times 10 is becoming 120. But please note that we can have negative values. If you want to work with bats, for example, okay, I can be less than this. Physically, it can be. And this means a negative value. Now, there is another version, not using intensity, but using pressure. And you know that when you have a wave and you have energy, it's related to the square of the amplitude. Both kinetic or both potential energy is related to the square of the amplitude. That's why you can find the definition of SPL, intensity, pressure, and this becomes 20. And that's the amplitude of pressure. For human ears is 2 times 10 to the minus 5 Pascal. By the way, the 20 here is related to the fact that the intensity is the square of the amplitude. Now, on this idea, you can develop other logarithmic scales. You can use it for stars and luminosity of the stars, or you can use it to measure the dynamic range of an instrument. It's the same idea. Or you can use it to take an amplitude of a seismometer, recorded on that, compared to a reference amplitude. That's Richter magnitude. Let's wait for Friday. By the way, this is the idea. Is it clear?
Yes.
Okay, please speak louder with an intensity that can be transmitted with an intensity larger than 10 to the minus 12 watts per square meter. So that's the idea. Can we go on?
Yes.
Okay, thank you. Now let's move. let's go towards let's say, oh, it's not moving here. I think I have a delay. Let me try to unshare because it's, let me leave for 1 second. Okay, something, maybe my connection is unstable. Please help me. Okay, let me try to share it again. My goodness. The HTTP network disappeared. And okay, maybe I can use, let me try to make an experiment while I'm speaking here. I'm trying to reconnect because I have only a Duron here. Oh, goodness. You should be able to look at me here. Okay?
Yes. Yes.
Okay, in the meantime, while I'm trying to set this on, do you have questions?
No, for now.
Or, okay, let me ask you one. Okay, maybe now network is working again, but ICTP signal disappeared here. Have you already been discussing aliasing and Nyquist frequency in other courses?
Yeah, I know the Shannon condition.
Okay, that's another case. But I'm speaking about courses here at ICTP.
No, Tarek, be specific. No.
Okay. So that's why usually I'm writing these things here. They should be very basic things, but I hope they are useful for you. It's a very general idea. Whenever you have a time signal, or you're using it also when you're using, I don't know, Photoshop, because you're doing filtering. And okay, it's resolution is related to resolution. Okay, here things are going to work again, but also with a network. I'm sorry for that, guys. So let me try to share again. Let's try to go towards the end of today's, because we have still to develop the idea beyond the new instruments. Now, since we have, let's say, about 20 minutes, I will go fast now because this is not a course about instrumental seismology, of course, by name, but I want to share with you some very basic ideas. I will leave to you your homework for Friday is to read the wordy slides that are here, that I've just been writing those things to be read. But let me go to one of the last ideas for today. And the idea is the following. Let's see if sharing is going to, oh goodness. Okay. So up to now, the keyword for instruments was inertia. Inertial, transfer function. Okay, then we have seen some technicalities about WWSSN, about digital recordings and stuff like that. The last step in instrumental seismology had been taken around the 80s, so it's okay. For you, it's old, for me, no. And it's based on a very simple idea that had been developed in let's say, in Germany and Switzerland by Wieland, by Streckeisen, and it was really a basic idea. Can we obtain an instrument with a flat transfer function? Because if yes, then we can use it for all the signals, not long period, short period. Okay, can we have just one? Okay, the answer is yes. Nowadays they are called broadband because they are flat over a huge range of frequencies. And it's based on this simple idea to have retroaction, a feedback. Now, this is the original sketch, and let me move to the next one. Let's imagine that we have a linear filter like our instrument, low inertial instrument. We know its transfer function, and we know how it's going to react to external forces. Okay, now let's create with a circuit, and that's That's why in the 80s it was possible, so that we can manage with a retroaction the answer. Now, let's imagine to create this feedback here and to apply a very simple filter, maybe plus or minus. Okay, the new transfer function can be written as a net one like that, because we have a feedback. Okay, so if you want to write the new transfer function, it's the original one, but modified by this. You could say, why we should create a feedback that usually is leading to nonlinear effects? Yes, but if we can handle it rapidly, there is a new parameter that we can play with. So if you're going to replace, instead of phi1, the expression of an inertial instrument, for example, and you write it, and you write it, and you have this k, and if you rewrite it, you have something like that. And you can say, so what? Well, if I can handle k very rapidly, I can change its frequency. What does it mean? That the effective resonant frequency of an instrument depends on a new parameter. And if we can tune it very rapidly, we can have a forced feedback instrument. What does it mean? Well, the idea is here, and it's called leaf spring, is that actually we have a system. Okay, let me play again with this ridiculous experiment. With a normal inertial instrument, I have to handle the oscillation of the mass. And I have to take care about that. And in any case, I have a specific resonant frequency. Now let's imagine that with a circuit, I'm measuring at any instant of time the force necessary for the mass to stand. In that case, I have no more motion. And in that case, each time by time, I understand the force needed to make the mass to stand. If I'm fast enough, I have something where nothing pretty much is moving, and I'm recording, instead of the force of the ground, the force necessary to stand the ground. That's the idea. So this sensor was becoming no more a passive one, but an active. Time by time, it's measuring the force. And this is what we have inside new accelerometers and very cheap ones, or inside the new sensors that are called the broadband seismometers. So the idea here now is, okay, now we have something that is flat. And that's easier to handle. Okay, in practice, it's a matter of circuits and mechanics. That's why I put at the end a couple of pictures of modern broadband seismometers, not the accelerometers that we have inside airbags, inside phones. You can buy for $10 now, and you can deploy them everywhere. But for, how to say, a scientific, professional broadband instrument, you can have a flat curve from very long periods to, let's say, very high frequencies, but they are actually professional ones, but they're much easier to handle than the traditional ones. That's the idea. Let me add, I'm sorry, but quickly, a few words. So let me jump to this so you can understand one thing here. There is a picture of a modern seismic station so that you have an idea here. And when you give a look to BB or VBB, it means broadband or very broadband. So the romantic vision of the WWSSN with those triplets of long periods or shorter periods, now actually they are replaced with sensors that are VBB, like these ones. And this means a flat response. A modern seismic station has also what they are called slow motion sensors. And I'm going to speak a couple of minutes about this. Then you have power distribution, communications infrastructures, going to satellites maybe, or to Wi-Fi or to new memory devices, you have some ancillary sensors, like, for example, GPS. So that's the modern view. I anticipated this slide here just to show you why I was showing to you, discussing with you very quickly the idea of broadband, because if you read a VBB, then you have a response that is pretty much flat. So that's a sort of a end of a story. I'm going backward now. And the actual situation that is evolving rapidly, in the digital era is that what we called WWSSN, now you can call it GDSN, now it's really global, and it's digital seismic network with number of stars that are increasing here. So in this brief history of seismometry, we started from the basic idea of an inertial instrument. Okay, Wood-Anderson, okay, magnitude. And we will see on Friday what's the consequence. WWSSN has become GDSN. But let me spend a couple of words about, let's call, simple concepts that we can easily discuss. Now, and this is a sort of a summary of a seismology course, we spent maybe hard and long time about the source. Okay, moment tensor is there when it's a point. Then we discuss a little bit about the structure, the Green's function. Now let's remember that every real record is recorded by an instrument. So we have a chain of filters. And what we are recording is this. So the first step to be taken is to deconvolve for the response or the transfer function of an instrument. But we know that because we built it. Could be hard, old instruments. Could be easier, broadband, let's say it's flat. But if we know the impulse response of an instrument, we can deconvolve and get the seismogram and move on to study the source or the structure. If you want to see a modern chain of a seismic recording, okay, remember that we have also, for those of you that are going to work on real networks, real instrumental seismology, that we have a chain inside also the instrument box, because we have a sensor, the seismometer, we have all the handling of a signal that still is an electric signal, but it's digital. And now the sampling rate is so short, and the number of bits may be so large, that we have a huge dynamic range, and maybe we have so many samples that we have to decimate it. Well, and that's one of the final concepts that I want to discuss with you today. It depends on the signals that you want to study, because we have a sort of extreme possible visions. Which ones? Okay, let me tell you. So the summary of this is, sorry, this was a sort of a prequel, but I'm sure that in this slide that I was skipping, well, actually now I'm not skipping it, but there is a sort of a resume that is running on the background of many courses that is called linear systems and Fourier transform. Here on the top, we have a definition of a linear system. It's characterized, and we discussed it also for differential operators that are linear. Okay, it's characterized by the property, the additive property, and the scalar multiplication property. That's the definition. There is also another concept that is the time invariant system. If your system is changing in time, okay, we're lost, we cannot work with that. But if yes, and if we have a linear system, we can study its response as to an impulse, Green's function, or in time domain, it's called the impulse response. You take its Fourier transform, it's called the transfer function. If you know this, okay, you know the answer, Green's function definition, to a generic input, because the output will be the convolution of the input times the impulse response, or in the frequency domain, the multiplication between the spectrum and the transfer function. If you want to input an harmonic function and not a delta, but a frequency, the linear response in time, it will be the transfer function to that specific frequency. So this was, remember that what we have been discussing, maybe since the first lecture, but definitely when we discuss the Green's function, and also today for linear systems, except the feedback, we are staying in the domain of linear systems and Fourier transform. And you've seen today how many applications, maybe trivial ones, they could be important in this domain. Now let me move to the final ideas. And now it's about the kind of seismograms that we want to study and which portion of them. For example, you may study body waves, like PES and all wave phases, and usually they are characterized by high frequency components. Or maybe you're going to study surface waves, larger, slower, dispersed. But if you imagine to separate them, you will see that the body waves domain is on the high frequency side, while surface waves are on the lowest, relatively low frequency side. This will be important on Friday, when we will see MB/MS. So please remember this. Other important thing, how an instrument is made. How an instrument is made will decide how your signal will appear. For example, here, we have on the top the recording by a broadband of a ground motion vertical component of a signal. And you see it's beautiful. You can see here some body waves, some conversions, some S waves, some messy things here, and then large shear waves beginning to be Rayleigh waves. But please remember that what you observe in a broadband can be filtered, and you may take the vision, the classical vision of long period and short period. Now look how different they appear. They are the same signal in the broadband domain, but when you filter it, imagining to work with traditional long period and short period instruments, they are totally different. Look at the frequency content here, but also the amplitude, because this has been magnified by 10 times. So please remember this. And one of the final digressions that I want to make with you is that, and this is maybe the second final message to you, is that when you're working with modern recordings, you could say, oh, that's easy, broadband, whatever. So we have all the frequency, we have many samples, we have everything. Yes, but please, let's use our mind first of all. Because, for example, a signal can be admired in the frequency domain, in the time domain, or in the acceleration domain, velocity domain, displacement domain. Now look at this. This is the recording of a very famous earthquake. Sometimes it's called Mexico City earthquake. No, this is Michoacan earthquake. It occurred 400 kilometers from Mexico City. But in September 1985, it destroyed and killed many people 400 kilometers away. And in one of the final slides of this course, when I will just touch the idea of site effects, just as an introduction of a concept that you will work out with Stefano Parolai, you will see the recordings in Mexico City. But these are recordings of the same event, but near the source. Now look at how beautiful they are. Acceleration, velocity, displacement. Please note the units. In acceleration, seismologists are using usually centimeters over square seconds. Engineers usually use G. Why? Because they can compare immediately with the gravity acceleration and the weight of a building. Velocity, centimeters per second. Displacement, centimeter or meters. If you remember the Japanese recordings of Toku, also with GPS. But please notice the different frequency content here. Very high frequency, intermediate frequency, long period. And what you notice here should be, you should recognize a good old friend. Well, not old, but 1 week ago friend, because that's the green function. It's the near field. Look how the seismometer was not going back to the equilibrium. The pen was tilted. That's the near field. And so when you listen to strong motion seismology, actually you're dealing with accelerograms recorded near the source, like these ones. And maybe in that case, you want high frequency, maybe beyond 10 Hertz. Remember that in seismology, the typical domain is between the longest period of the Earth Am I alone here? Tarek, Dung, what is it? What is the longest period of the three modes of the Earth? S02 is 54 minutes. So the longest periods of seismic motion are related to the three modes of the Earth, and they have a period of thousands of seconds, right? Yes. Are you awake? Okay, good. Now, typical global seismology, let's say 100 seconds up to 1 second. Local seismology or strong motion seismology, you can go from 1 second to 0.110 Hertz or higher. That's why in some cases we're still using accelerometers. And that's why in one of the final plots that I was showing to you, there are also strong motion sensors that are accelerometers. I've left you toward the, okay, we are finishing pretty much on time here. But please, if you're going to work with strong motion seismology, in the 80s, that was meaning something that had a sort of a clear definition, because it was something that was causing strong shaking. Now, strong shaking, what does it mean? What is strong? Well, strong means that can cause damage. So it's for earthquake engineering studies. So actually the goal of strong motion seismology is trying to understand signals that can be used in earthquake engineering or engineering seismology. I'm working in that, but I never understood exactly what is the difference. Depends if you're an engineer or a seismologist. At the beginning of the definition of this strong motion seismology, we had in mind the classical instruments. So the idea was to consider signals that were around, that could go to 1 G of acceleration, going without scale, not going out of scale. But nowadays, the sensors have such a large dynamic range that we can also record tiny movements. So actually, the border between strong motion seismology and instruments and traditional one is fading. But traditionally is, okay, working with accelerometer sensors or very broadband. Very broadband can cover most of the frequencies, and accelerometers can help to use broadband. So there is not anymore this distinction. And actually nowadays, the distinction, and okay, let me close with the last 2 slides. I'm not following exactly the order, but I'm trying to follow a sort of a logical order in my storytelling here, is that the summary, maybe, of what we discussed today is in this picture. Here, what we can see in the left picture is we have a range of periods that is really large. We have orders of magnitude here, and it's going to very long periods to very short ones. Okay, here it's the realm of acoustics or ultrasound. And that's why here we have high frequency seismometry, usually used for engineering applications. Here we have the three modes of the Earth that are so long that actually are going towards geodesy. And these gray bands here are showing what was the operating range of WWSSN or standard instruments. And here you see equivalent Earth acceleration. Look at the definition with logarithm, because we want to squeeze scales here. Of course, it's using from 0 to minus, so you have to revert the definition, but it's the same. So look at the gray part here, the gray zone, and look at the new one with VBB and maybe with stern motion sensors. It's really so large that you can go to from geodesy, that's why GPS can be included here, to, let's say, sonic equipment. And we can go from very tiny motions to very strong ones. But let me conclude with two things here. First, you see this sort of a bottom end here, is that we have to remember that how much sophisticated our instruments could be, we have noise. Now you could say, what is noise? Well, noise is what is not signal. So noise could be acoustic noise in a room, like a fan or people talking in one corner. Okay, what is a signal for seismology? Well, the recording of an earthquake, isn't it? Yes, and so everything else is noise. And noise, what is coming from? Well, could come from nature. For example, waves shaking on the coast. It has been first recognized in Uppsala, in Sweden, in the 60s, because the sea was shaking the coast, and there was a noise there. You can call it microseisms. Or there is human activity, factories, traffic. Okay, it's more related to anthropic effects. It's more, you can call it microtremors. You can have wind shaking the trees with the roots. Depends on the scale. Well, let me tell you one thing. That's noise for classical seismology. But in many cases, you're going to work with noise as a signal, because there is a theory, a very nice one, that you can recover the Green's function of a medium studying noise and cross-correlating it. So in many cases, you're going to take seismic recordings and throw away the earthquakes because you want to use the noise. So please remember that the distinction between noise and signal could be subjective. This was one of the final messages. The second one, and it's the last one, but is a bridge for the next lecture, is that we would like to have here a measure telling us, okay, we have the amplitude of the motion of the ground, but we would like also to associate it with a measure of the energy of an earthquake. Because if we are 100 kilometers from an earthquake, from a large one, or we are 10 meters from a small one, maybe we can get the same amplitude, maybe with a different frequency content. But how to scale this? And this was one of the problems that Richter, as I was telling you, was facing. The press, the news, okay, was that a strong one? Well, so he created a measure that is trying to synthesize this with a number. That number was called magnitude, coming from astronomy. And that's why here you see on the top and on the bottom, what are the limits? But on average, because it depends on our distance to the source. And that's why you see magnitude 9.55. And here you have an older, maybe not so nice picture, but it's showing again the range of frequencies that we have to work with, the amplitudes that we have to work with, And according to the instrument, accelerometer, typical network station, the noise here, we have many lines that depend on our distance from the earthquake. That was the idea that Richter developed to define magnitude. Magnitude definition actually is based on an idea very similar to the definition, please look me in the Stasi cam, about decibel, about sound intensity level, about dynamic range, to use logarithm to squeeze amplitudes, to squeeze scales, and to use a reference, a sort of a reference threshold. That was the idea that he developed. We will study that on Friday in a couple of slides, but that's the idea that he was coming from. And final slide, it's an old one, just to tell you that what we have been discussing, and we are going to discuss in this course here, is mainly here. And this picture was taken, sorry, but we are going to conclude in 1 minute. This picture was taken when GPS, they had in the 80s a sampling rate that was too large to be used in seismology. But nowadays, you can take this line and go with a solid one here along. So there is no more a solid border between seismology and geodesy, Alessandra Borghi's course, and there is maybe no border between still motion seismology and acoustics. So that was another final message. And anyways, also between noise and signal. Well, there is a distinction, but it depends what you want to study. Okay, so my guys, it's the end of this, I hope, relatively nice trip around very different concepts about. So I've been using the idea of the history of seismometry, but to recap again the concept of a harmonic damped forced oscillator, because we are going to rediscuss it on Monday using a spring and a dashboard, but for a totally different definition. It will be viscoelasticity. And on Friday, we're going to develop some ideas coming from instruments, wave fields, and the history of seismometry to better develop the idea of magnitude. Okay?
Okay.
I hope you're still awake.
Okay.
The only homework that I'm asking you is to read the wordy slides that I left through them just to explain what we already discussed. So inertial, transfer function, broadband, digital, era. Remember sampling. Maybe you don't have to care anymore, but please remember. Okay?
Okay.
Yes, Professor.
Okay. Yes? Any question? Well, you have always time to ask on Friday. Okay?
Okay.
Okay. You should have all the material that we are discussing together here on the two Moodle websites. Please tell me if not. Okay?
You have it. It's there.
Yes, from Unit 3S, yes, I have the information.
Okay, good. So my friends, good afternoon, good Thursday, and let's meet again on Friday. Okay?
Thank you. Thank you. Bye.
Goodbye.
Goodbye.
Bye, Professor. Bye, everyone.